Okay, welcome to the second lecture in week 3 of Machine Learning Foundations. In this lecture, we'll understand the concept of orthogonality and orthogonal subspaces. The build-up for the idea is that once we understand orthogonality and orthogonal complements, we'll be able to understand what one means by doing orthogonal projections, which is coming in the follow-up lecture. And these two will lead up to understanding least squares problems, least squares problems which are closely tied to projections, understanding projections. So in this lecture, we will understand what it means when we say two vectors are orthogonal, and what does it mean to say two subspaces are orthogonal, and we'll also characterize orthogonal subspaces. I mean, we'll take the four fundamental subspaces we had earlier, which is the column null space, row space, and left null space, and try to understand which vector in which space is orthogonal to which other vector in another subspace. So which subspace is orthogonal to the other in terms of the four fundamental subspaces. That's something that we'll understand in this lecture. Now I needed these four subspaces simply because I wanted to move on to the very new topic, which is build up is to look at least squares, and for this I need to cover background material on orthogonality. Which is what I'll do, and then look at projections. So the idea is to look at what it means. So coming next, so what we are going to look at, we will look at one orthogonal vectors, length of a vector. Two will look at projections, and then this leads to least squares problem. This is what we'll get to. So this is the order we'll look at. We'll start with orthogonality. What it means to be a length of a vector. This is something you must have looked at before. Doing a quick recap. Let's say imagine you have some vector 1 and 2. So this is the vector 1, 2 that I have drawn to the best of my abilities. So what is the length of this? What we do is x1 square plus x2 square, which in this case, so square equals 1 square plus 2 square equals 5. So that's the intuitive notion of a length. So in general, if you have a x belonging to Rn, for x belonging to Rn, the length of x is defined like this. For x equals x1 until xn belonging to Rn. This is the length. Now the next notion is when are two vectors orthogonal. Orthogonal vectors. Can say that x is orthogonal to y if x transpose y equals 0. Here this is called the inner product or dot product in some books. So if x equals x1 up till xn, y equals y1 up till yn, then x transpose y is summation xi yi, y equals 1 to n. Now this definition coincides with our notion of a right angle triangle or Pythagoras theorem. So recall what you have from Pythagoras theorem. From Pythagoras theorem, if you have a right angle triangle, say x, y, x plus y. So this notion of right angle is that, you know, this plus this equals x plus y square. Now if you expand this using our definition, this is the same as x transpose x plus y transpose y equals x plus y transpose x plus y, which is the same as x transpose x plus y transpose y plus x transpose y plus y transpose x. Now this goes off, so you get 2 times x transpose y equals 0 implies x transpose y equals 0. This is the same as saying orthogonal. X is orthogonal to y. Just a quick remark. 0, 0 is orthogonal to every x. First claim. The second one is if the vectors v1 to vk are mutually orthogonal, then it's a linearly independent set. I mean, this is easy to show. Why? I mean, let's see why. Simply because let's suppose some linear combination of these vectors leads to 0. Say c1 v1 plus c2 v2 plus blah 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 ck vk equals 0. Now if I take the dot product with v1 on both sides, get 0. This implies c1 into v1 transpose v1 equals 0, but it's not 0, implies c1 equals 0. Similarly, Ci not equal 0 for all I. Let me put it like this: mutually orthogonal non-trivial set of vectors. So these are not the 0 vectors. So assuming 0 is not part of this, so then we get this. That's the end of this claim. You can just look at a quick example about example. The standard basis says 0, 1, 0, 1, 0, 0, 0, 0, 1. These are orthogonal vectors. It need not be standard, you can make up other examples also. For example, this 2, 2, 2 minus 1, 2. Yeah. Now we have another related concept called orthonormal vectors. Which is u comma v orthonormal if they are orthogonal and of unit length. So this is orthogonal, this is unit length. So again, an example is 0, 1, 1, 0. Another example is cos theta, sin theta, minus sin theta, cos theta. These are two examples. Now once we have defined orthonormal vectors, orthogonality, we can also look at what is called orthogonal subspaces. So if you have two subspaces u comma v, so I am going to use capital letters for subspaces, small letters for vectors. So u comma v are orthogonal subspaces if x transpose y equals 0. So if I take anything from u and any other vector from v, and if I take the dot product, it has to 0. This is like for all x belonging to u and for all y belonging to v. Now again we can look at some examples. So the first example, obvious trivial example, is take vector 0, it's orthogonal to every subspace that you can think of. So define u is as the span of 1, 0, 0, 0, and say 0, 1, 0, 0. Suppose this is view, and then say v is something else, say 0, 0. You take the last two coordinates. Then u is orthogonal. Okay, need some more space. I mean, V is not the only orthogonal subspace of U. You could make up another one. if I write say W equals span of 0 0 minus 2 1, then W is orthogonal to U and W is orthogonal to V. Orthogonality with respect to the 4 fundamental subspaces of a matrix. So the first claim is, if I take the row space of A, then it's orthogonal to the null space of A. And the proof is fairly straightforward. If I take X belonging to null space of A, then it just means that Ax equals 0, which is like writing say row 1, keep running out of space. So A is M cross N. A is M cross N unless specify explicitly it's a square matrix. Assume it's some M cross N matrix. So you have row 1, row 2 until row M. This is A, and then you have x1 until xn. This is the 0 vector. The equation above implies row 1 is orthogonal to x, and row 2 is also orthogonal to x, and so on until row m is orthogonal to x. That's amply clear because you're taking dot product here. I don't know how to highlight. If you take the dot product here, so row, then what you're getting is 0. So row 1 is orthogonal to x. If I take row 1 dot product with x, then I'm getting 0. So row 1 is orthogonal to x. Similarly, row 2 is orthogonal to x, and row m is orthogonal to x. Then, thus, any linear combination say C1 row 1 plus C2 row 2 and so on plus Cm row m, this will be orthogonal to x. And this belongs to the row space of A. So, if I take the row space of A, it's orthogonal to null space of A. Which is the same as writing, or equivalently, column space of A transpose is orthogonal to null space of A. Now, the same thing can be written like this: column space of A is orthogonal to null space of A transpose. Okay. You could do a much shorter proof. I am going to skip the proof. Follows from claim 1. Okay, let's look at an example. and end this discussion again. So what is the rank of A, which is the dimension of column space of A? It's obvious that the second column is just 2 times first column. So the dimension of the column space of A is 1. And if you want to look at what would be an entry belonging to the null space. So if I set x equals minus 2 comma 1, then this belongs to null space. It's fairly simple. Take minus 2 times the first column and 1 times the second column, that results in the, since column 2 equals 2 times column 1. Now again we can look at the row space R of A is just the line through. You look at each row. First row is 1, 2, second row is 2 times the first row, third row is 3 times the first row. So this is really one row that matters. The other rows are just scalar multiples of the other row, first row. So the row space is just the line through 1, 2. And null space if A is the line through minus 2, 1. Now if I take if I look at 1, 2 into minus 2 comma 1, this is equal to 0, and that's just this verifies row space of A is orthogonal to null space of A, because I took an entry here and 1, 2 belongs here. Yeah. So I took an entry from the row space of A, a vector, and I took another vector from the null space, and their dot product led to 0. So they are orthogonal. Yeah. You could check this even for the other two spaces. So if I look at column space of A, it's just the line through 1, 2, 3, and then the null space of A transpose is a set of all y's such that y1 plus 2y2 plus 3y3 equals 0, and this is not a line, this is a plane. And why this is true, this is set of all y transpose A equals 0. And this y transpose A equals 0 is the same as, column space of A is orthogonal to null space of A transpose. Yeah. Yeah. So think about this. Connect this to the claim column space of A is orthogonal to null space of A transpose. Yeah, we could check the dimensions, dimension check. Dimension of column space of A transpose plus dimension of this should be 2, so this is the number of columns. This is the number of columns, and this is 1 and this is 1. Now dimension of column space of A transpose is dimension of null space of A transpose. This should be the number of rows, which is 3, and this we know is 1, this we know is 2, this is the number of columns. Okay, though that's where I'll end this lecture. We'll next look at projections. Okay, so before we end this lecture, we'll have a brief recap. What we learned in this lecture, first and foremost, is the simple concept of length of a vector. That's something we learned, and then we understood what it means to say two vectors are orthogonal. And we also understood what it means to say one subspace is orthogonal to another. And using this notion of orthogonal subspaces, we were able to understand the 4 fundamental subspaces well. In particular, we were able to show that if I take the row space, any vector in the row space, then it's orthogonal to any vector in the null space of a given matrix. So these 2 subspaces are orthogonal. Along similar lines, we were also able to show that any vector in the column space of a matrix is orthogonal to any vector in the left null space of the same matrix. And so we understood this. We were able to show this 2 claims, and also we worked out these 4 subspaces, and also understood that by characterizing the basis, we were able to infer that the 2 claims that I just said, which is the row space is orthogonal to the null space, and the second claim, which is column space, is orthogonal to the left null space. We were able to verify this through an example. In the next lecture, we will be looking at projections, and that will lead up to the least squares problem subsequently.